Hi, everyone. Welcome to the Spring 2021 Core Facility Seminar Series. Today, we'll be featuring the Electron Microscopy Facility. A quick introduction, I am Lisa Korpieski, the Director of Communications and Marketing here at the Institute for Applied Life Sciences. In today's seminar, you will hear from Alex Ribbe, the Director of Electron Microscopy, as well as being a Senior Lecturer in Polymer Science and Engineering. Our guest speaker is Satyam Srivastava, a PhD candidate also in PS&E. We hope that with these bi-weekly seminars, you will discover what great resources that the centralized UMass Amherst core facilities offer to our campus community, the New England region, and beyond. And just a few housekeeping items. The seminar is being recorded. If you miss any part of this seminar or would like to forward it to someone who could not attend, there will be a replay of this and all previous seminars in the series on our website. A link will be put in the chat. I recommend you set your view mode to speaker. Please stay muted during the talks. We will save the Q&A until the end of the presentation. During that time, I welcome you to unmute yourself and ask your question. And now I'd like to introduce you to Andrew Bernard, the Director of our centralized UMass Amherst core facilities.
Thank you, Lisa. Welcome, everyone. Thanks for joining today for the fourth seminar series of the Spring 2021 Core Facilities Seminar Series. As Lisa mentioned, my name is Andrew Bernard. I'm the Director of our centralized core facilities here at UMass Amherst. In case you haven't worked with us, a little bit about who we are. Our state-of-the-art labs, instrumentation, equipment, and most importantly, world-class experts are helping researchers drive discovery and pursue scientific endeavors across all disciplines. The cores here at UMass Amherst are open to anyone from students through senior scientists, regardless of your affiliation, including researchers from other academic institutions and our commercial partners. To help access our cores, there are several funding opportunities. For those who are IELTS investigators, you have access to core credits and center seed funding. For our external partners, the the Mass Innovation Voucher Program subsidizes usage for small companies who are headquartered in Massachusetts up to 75%. To date, this program has awarded more than 500 vouchers, representing a total of over $5 million in project costs across all 5 UMass campuses. We're here to be your partner, and we aim to expand your research capabilities and productivity. If you have any questions about our capabilities or technologies, you're welcome to reach out to me directly, to any of the core facility directors, or to check out our website where there is quite a bit of information. It's now my pleasure to introduce Dr. Alexander Ribbe, who is the director of our Electron Microscopy core facility and also a senior lecturer in the Polymer Science Department and Engineering Department. In addition to directing the Electron Microscopy core, Dr. Ribbe also oversees the atomic force microscopy and X-ray scattering cores. Dr. Ribbe joined UMass in 2010, and he's been leading electron microscopy efforts here on campus and beyond since that time. We're grateful for Dr. Ribbe's contributions, and we are grateful to have him as part of both the UMass and the core facilities community. With that, I'll turn it over to Alex, and we'll be here for the Q&A. Thank you.
Thank you, Andrew. Everybody can hear me?
Loud and clear.
Yes.
Okay, good. So, well, like Andrew said, I'm the director of the electron microscopy at UMass Amherst. And I thought I'd give you first a little bit overview of our team and so what our backgrounds are. That helps if you want to talk to us. So I assume. So I got my PhD in Germany at the University of Bayreuth in transmission electron microscopy, specifically energy filter transmission electron microscopy. And technically I have a PhD in chemistry, so which is specialized in polymer chemistry. I spent almost a decade after that in Kyoto at the University of Kyoto. And I kind of did the same thing. On top of that, I started learning about AFMs, confocal microscopes, and small angle X-ray scattering and X-ray diffraction. So, and then about 10 years later, I moved to Purdue University, where I obviously continued the same thing, but I added on working on small angle neutron scattering at the Synchrotron and Argonne National Laboratory and the small angle X-ray line on the synchrotron. So then about 10 years ago, I moved to UMass Amherst, but since then I'm running the electron microscopy. There wasn't at the time when I came, so we consolidated all instruments which belong to material science and the biological sciences into which you see now, the electron microscopy core at UMass Amherst. So we have one technical staff member. His name is Ribbe. He's in the facility since the beginning. The beginning was quite some time ago. So he has a background in biological sciences, And he's really good. He's running the day-to-day operations on TEM and SEM for basic training. And he is really good at ultramicrotuning, which is one of the core sample preparation instrumentation we have. And then recently, since last year, we have another staff member who's kind of partially electron microscopy. His name is Keith Dussault. He has a PhD in chemistry as well. He worked for 2 years at R&D laboratory in Dow Chemicals. And then after that, he got his PhD at UConn in hard materials. And he complements us very wonderfully. So he has a background in SEM, EBSD, EDS, focused ion beam. So he's helping us with that in the electron microscopy core. He is working in the AFM core on nanomechanical properties. And he has a background in lithography. So he's helping in the clean room with a e-beam writer. Okay, wrong button. There we go. So it's what I said. So it's in the previous slide already said what we are doing. Just a little bit of an overview. We have about 10 instruments, sample preparation instruments, which is mostly ultramicrotomes, sputter coaters, plunge freezers, and so forth, things you need. And since we cover literally all facets of science, we deal with soft materials, biological materials. Well, I call it biological materials. It's basically life sciences, and hard materials as well. So then we have 3 transmission electron microscopes currently running. We can do high resolution TEM, we can do scanning transmission as TEM, we can do high angle and dark field, we can do energy filter transmission electron microscopy, EELS, EDS, tomography, and we can do CryoEM. I put the CryoEM a little bit in a different pot here. So because CryoTEM, I will talk about that a little bit later, has very many different ways of looking at. So then we have currently 2 scanning electron microscopes. We added a variable pressure scanning electron microscope just last year, so which will be able to do serial sectioning and 3-dimensional reconstruction, and also do cryo-SEM, so we can observe samples at cryo temperatures. On top of that, we provide data analysis support and everything that is related somehow to electron microscopy. So, transmission electron microscopy, first thing people think about is atoms, right? So this is the most common question I'm asked, can you see atoms? So yes, to some extent we can see atoms. So as an example, I put up here perovskite crystals, which is mostly made of lead. So on the left side here, you see a high resolution transmission electron micrograph, and you can see the lattice of that crystal. So the spacing between those lines is somewhere in the 2 to 3 angstrom range. So those lines are created by by something called diffraction contrast of that crystal. On the right side here, you see a high angle angular dark field image, which is a method applied in scanning transmission electron microscopy. And here you really see the atomic columns of the lead here. So if you look very carefully, you can see white dots in here. So this is one thing. I consider that hard materials. Perovskite is a hard material, but it is mostly used right now in type of composite materials for hopefully someday be useful in photovoltaic devices, which are solar cells. So then example about soft materials. So what you see down here is a tomograph of and it's supposed to rotate. It doesn't. Why doesn't it rotate? Oh no. Okay, so this is the 2200. This is our biggest transmission electron microscope. And this one here is ultramicrotome film of a dipole copolymer, and one phase has been removed. So this 3-dimensional model. This has been created by a tilt series of about 100 images, which afterwards, with a certain algorithm, you can recalculate on the actually 3-dimensional structure. And if here we go. It doesn't allow me to do this with the laser. So this is what people appreciate. So you might think, oh, it's just a sponge, but that's just a sponge. The whole diameter in here, the pore diameter, is about 10 nanometers. So is for most people who know that this is really small. So things like that, you might be able to use in gas separation membranes and things like that. There's application you can think about. And this is what electron tomography can do for you. There we go. Okay, and then the third example I put on here in terms of transmission electron microscopy is CryoEM. So CryoEM is a big field, but nowadays CryoEM is referred to generally as that what people think is what is single particle reconstruction. So what you see on here has nothing to do really with single particle reconstruction, but it's still CryoEM. So this is a polymer vesicle which carries protein, which you can use for drug transporters or similar, or well, technically for drug transport. So this over here is a classic CryoTEM image. This is plunge frozen in water. This is in vitrified ice. And what you see here is those little bubbles. So those little bubbles are somewhere between 20 to 13 nanometer in diameter. They carry a polymer shell, and inside, in that case, is cytochrome C. So cytochrome C contains iron. So while in this mode here on the microscope, we don't have a high-angle anode dark field detector, we don't have an EDS detector and things like that. So we can move the same sample into the big scope and just prepare it a little bit different. So namely, we just drop cast it on a carbon film and then freeze it in the microscope. So this was good enough. It actually destroys that particle to some extent, but still we can make out the cytochrome C within the particle, which is those white dots. And the reason why this is bright is because of the iron in the cytochrome C. So we could prove that this one is iron by EDS as well. Okay, so as I said, CryoEM. We can do some kind of CryoEM, and there's certain CryoEM we cannot do because of the lack of instrumentation. So I will explain you a little bit what we can do. So we can do cryo-ultramicrotomy of soft materials. We can do plunge freezing. So we can do cryotransfer into one of our TMs. So that's what you saw before. We can image vesicles, micelles, and so forth. We also can use proteins. We just couldn't do single particle reconstruction, which requires a special TM in order to accomplish that. So you can also just freeze the sample inside the TM, what you saw before as well, which is technically also CryoEM, but this is not what people technically refer to at this moment in time. And we have CryoSEM over here. So there's several sample preparation units are required typically in order to biological materials, for instance. So, but we still, since we have a CryoSEM capability now, we can freeze samples in the SEM. So we also can cryo-ultramicrotomy sample, move them into the SEM, which could also be plunge frozen first in order to accomplish that. So there's several capabilities which are very interesting, and we haven't really fully explored yet, but this is things which are available right now. So I made this box around this. So this is kind of my world where I'm coming from, so you understand kind of my way of thinking. This is what I got my PhD in. So that's what I did: plunge freezing cryo-ultramicrotomy of soft materials, CryoTEM, and then so just using frozen sample and observe them in the TM. So you might think, what has all of that to do with particles floating on a liquid and observing that in an SEM, right? Because first of this one is all frozen, right? So, but we do a lot of ultramicrotomy, as you might have realized, and this is what an ultramicrotome looks like. So you put your sample in here, typically in epoxy. If you have a polymer material, that's kind of more convenient since it's already a polymer to begin with. You don't really have to embed it most of the time, and then you cut it. So if your sample is too soft, you have to cool it down to cryo temperatures, otherwise you can cut it. It's like everybody who ever tried to cut like soft butter would know that you can't get a thin slice of it. It's technically the same idea. So if you do it at cryo temperatures, you can literally only, if you go very low, have to catch those little plastic slices which are 50 nanometer thick on a grid here, which then ultimately moved into the electron microscope. And you can imagine this is really hard. But it's still done on a daily basis, but it's really difficult. So you need a lot of experience, you need a lot of patience, and you need a really quiet hand and a lot of time. So we came across something called ionic liquids. So ionic liquids are liquids which are basically salts, which are in liquid form. They can't crystallize. So those ionic liquids have some very interesting physical properties. One of that is they have very low melting points. So this particular ionic liquid, what we used here, we used for ultramicrotuning. So we took a polymer film, we filled that there's a gel liquid in here. And when you cut, you can actually float those little films of your sample on the top of that liquid. And then it's actually easier to catch that with a grid. You just take the grid, you put it on top, and it will absorb to your sample holder, which is very nice. And that stays liquid until this low temperatures which we require in order to cut certain samples. Now, we got all excited about that. And you might wonder, wow, why can you get excited about something floating on something? Well, there's a point to that. Because those ionic liquids, they have a second property, which is they have literally no vapor pressure. So let's back up a little bit. What does this have to do with the SEM? So we have two scanning electron microscopes, as I said. We have a high resolution scanning electron microscope, which is a Magellan. And then last year we got the Thermo Fisher volume scope, which is based on the Cryo platform, which has a built-in ultramicrotone. That still doesn't really explain technically the ionic liquid stuff, but so SEM typically is known for providing very beautiful three-dimensional images. So this is what it's kind of famous for, I believe, in general. And this is usually what people ask for. Oh, can you make that really beautiful three-dimensional images for you? For me, well, this is fair. This is fine. So you get something like this here. These are latex spheres. And so you have to look at the magnification. This is already 100,000 times. So these are 200 to 300 nanometers. And you can see a lot of details actually on those particles. And this is an SEM with an uncoated sample. So it's a topographical method. So you can directly measure X, Y. You can measure distances, but you actually can't measure height. You can, but it's really difficult. You have to go through a lot of hoops. And technically, SEM is a high vacuum method. So you go down to 10⁻⁵ to 10⁻⁶ torr. And water, for example, instantly will evaporate at that kind of pressures. On top of that, it's considered really slow because it's a scanning method. So if we live with the fact that the image is actually not that good, we still can extract a lot of information out of actually images which might be considered as bad electron microscopy images or noisy. So I took a series of images of those latex spheres, and I changed the scan time, which is literally just the time I acquire signal from the scanning process. So this is a very fast frame. This is 25 microseconds. One line is 25 nanoseconds. So you can see the particles, but well, this is not really a picture you would consider, oh, this is a really good SEM picture. So as I go up in acquisition time, I get something which looks more like spheres, more something like people would look for. But from a scientific point of view, there's no really reason why it has to look like that. The square in the back is something called the contamination square. I left it on purpose because it doesn't bother either for that what we want to do. So if you just want to know where the particle is and where the distance is, it doesn't matter whether the image is good or bad. You still can extract it. You can even extract it from that kind of image. So what does this provide? That provides speed. If you want to image particles in an electron microscope and you want to image it on a liquid surface, well, you need speed. So this is what speed provides is by sacrificing image quality, so to say. So, and then this is where our ionic liquids come in. So we put ionic liquids into the electron microscope, and since they have virtually no vapor pressure, they will not evaporate, even on the 10⁻⁵, 10⁻⁶ torr. And because we were so excited because this polymer film was actually floating with an ionic liquid, we were hoping other stuff would float on that as well. And it did. So this is kind of the summary what I just talked a little bit about. So the primary goal is to just measure the location of the particle rather than providing a beautiful rendered three-dimensional image. So we want to have the relative location. One nice thing is about the method which we applied is that the very fast scanning also minimizes charging naturally. Because the faster I scan, the shorter the electrons will be exposing a certain area of the sample. Then the sample, it's good if the sample is a little bit conductive. The nice thing is ionic liquids are a little bit conductive on top of that. So everything plays into kind of positive trend for these materials. And as I said, they will not evaporate under high pressure. So now Satyam will now talk about what he did with ionic liquids and our high resolution SEM and what kind of really, I think, outstanding data you can extract from that. Yes, so I give it over to Satyam. And if you have any question. Okay, so I stop sharing the screen.
Hello everyone, I am Satyam. I am a PhD student in Professor David Hoagland and Professor Thomas Russell's group. And today I will talk about how we use electron microscopy to study assembly and dynamics of nanoparticles on liquid surfaces, especially anisotropic rod-like particles. So the overall objective of this study is to observe nanoscale features using a high resolution technique like electron microscopy in solvated systems, where due to the resolution limit, we cannot use optical microscopy. For example, nanoparticles at liquid-liquid interfaces, gels, and solution crystallization. So these are some of the systems I have looked at, but in particular, I will talk about nanoparticles assembly. So why we are interested in, so I have a brief background. So assembly of solid particles at liquid interfaces has been for a long time. Solid particles stabilize small emulsion droplets in case of a Pickering emulsion by reducing the interfacial tension. And to speed up this process, our group used nanoparticles which quickly go to the interface and can form these jammed assemblies. So that stabilizes a non-spherical liquid structure, as shown here in the schematic liquid tubule, and that enables printing liquid structures in liquids that we call liquid in liquid 3D print. And now anisotropic particles like cellulose nanocrystals can also be assembled at center. But nature of these assemblies is not very well understood. So while the simulations will predict in a planar assembly, we can get a lot of order orientationally, and we can have liquid crystalline phases. The question is, can we get these orders in case of an interfacial assembly? So, but there are additional factors like what is the orientation of the particle at the interface, how they absorb there, and what is the interaction among them. So these are some of the questions which we want to answer. And we need a local visualization technique for this because these are local events. So if we had microparticles, we can use optical microscopy using a Langmuir trough. We can spread the particles over a non-solvent and then study it using the microscopy by compressing the system and studying the order. But we are interested in much smaller nanoparticles, and there we need a better resolution. So for that, we want to use a scanning electron microscopy. And if we look here on this figure in the right, it shows that SEM has a very good spatial resolution, but it also has a good temporal resolution. although this figure doesn't include ultra-fast microscopy techniques. So it's good for studying the dynamics at millisecond or microsecond time scale. But the challenge is that most of the liquids are not stable in the high vacuum condition of the electron microscope. So that brings us to the ionic liquids, and as Alex mentioned before, that these are salts which have low melting point, and it can be close to or below room temperature, because these have either a bulky cation or a bulky anion, which prevents them from crystallizing. And the other important characteristic is the high ionic conductivity of these ionic liquids, which enables us to do imaging without having charging artifacts. So previously, it was found that it's compatible with high vacuum techniques like SEM, and was used as a coating to prevent charging. So in our group, past group members developed this procedure where we use scanning electron microscopy and ionic liquids as they are non-volatile and conductive enough. And with that, we can successfully capture motion of nanoparticles on the surface of a liquid. So this is ionic liquid, and we are looking at the diffusion of 170 nanometer silica nanospheres. And the particle motion can be tracked with single particle tracking, like in case of an optical microscopy, and then from their trajectories, the diffusion coefficients can be calculated. So that, and if that is compared with the calculated diffusion coefficient, it's in agreement. So here the particles are in a thin liquid film, a freestanding liquid film, but the concept remains same, that we are looking at the surface of the liquid, and we are looking at the diffusion of these particles, which are much smaller than the particles which are previously looked at with the help of optical microscopy. And also in past, in particular, Dr. Iga Gao and Paul Kim, past group members, they fabricated this device, which is our setup to replicate a Langmuir-Trauf type of assembly, where we can control the volume of a droplet in situ inside an electron microscope, and control the areal density of the particles. So here we are looking at a movie taken inside the electron microscope, and as shown here in the figure in the right, the areal densities can be changed from a jammed state to a dilute state, and again to a jammed ordered state. So that enables us studying these particle assemblies with different areal densities, and study their order present. So now what I am interested in is rod-like particles. And our model system is this gold nanorod coated with silica, so that we can covalently functionalize different ligands, specifically polyethylene glycol. And we synthesize these with different aspect ratios, and the sizes are roughly around 40 nanometers in width and 100 to 200 nanometer in length. And the sample preparation is very simple. If the particles can be dispersed in ionic liquid, they can directly spread on a silicon wafer and can be put inside the electron microscope as any other sample without any confinement. Because as we are interested in interfacial assembly, we want to avoid any kind of confinement which can affect the interfacial behavior. So here we can look at motion of a single nanorod. So we can track the center of mass motion. We can calculate translational diffusion coefficient. We are still figuring out how to track the rotational motion. These particles have a very fast rotational motion, faster than the frame rate we use usually for the image. That's something we are working on. And the other thing we noticed that these particles are strongly bound to the interface. So we don't get any desorption process during the observation. So we have very low effect of or any effect of electron beams. So we don't observe any artifact during the imaging, as we are working with very low electron doses. And we can then study evolution of the assembly with the time, and we go from a dilute state to a denser state as more particles come to the surface and absorb there from the solution. And we can observe different local features present in these assemblies. And we can track the dynamics at these stages, different stages. But obviously we cannot take a movie from the beginning to the end because it's an extremely long process, and we want to minimize effect of beam. And we are getting a very good contrast here because we have a gold core, but we also get a decent contrast when we have pure silica particles. So the contrast is not a problem with this imaging. And then at the final stage, the assemblies are jammed, so we get a clearer picture, while in case of the dilute assembly, because particles are still in motion, we get a picture where rods are looking wiggly. And we can then study this same process with different aspect ratios to understand how much order we get if we change the shape of the particle. And we observe that we get more local order when we have higher aspect ratios. And we can calculate different order parameter by identifying the position and orientation of each and every particle. So as we can identify orientation of every particle, we notice one feature that many of these particles are not lying flat to the interface. So which is obvious for a high density assembly, where some particles coming up from bulk can't absorb to the interface fully, and we can identify them by contrast variation and SEM imaging depth. But interestingly, what we noticed that we can also sometimes capture these rods which are partially absorbed even at low areal densities where particles are still in motion. So that suggests that the absorption process of these rods is slow. So it's known for the larger particles from previous studies by other groups. And the reason is that when particles absorb to the interface, the liquid contact line has to advance over the particle surface, and that can be pinned and can be slow. But the fact that we can observe it using electron microscopy, it suggests that this technique is working very well, and we can even observe these features which involve very small energies and can be affected by the electron beam also. So by reducing the electron doses, we can observe these local features and can study this extremely fast process where a single particle is absorbing to the interface. So this is one of the reasons why we have so many particles which are out of plane, because this process is small and many of these particles don't absorb fully to the interface when system becomes dense. But what else we can see is that we can observe the interactions among the particles. So when we look at slightly denser systems, we notice that particles tend to stick to one another directionally. side by side. So capillary type of interactions usually explain this behavior for much bigger particles. These are much smaller particles around 100 nanometer or less in dimensions, and it would be expected that such forces would have a very small effect on these particles assembly behavior. But what we see is that we get a very significant effect of this capillary forces on the assembly. There is formation of these stacks which grow further with time, which we can see, and then ultimately lead to this type of morphology where we have local order but not global alignment. So this is a important detail for us, which helps us understanding how we get the order in the final assembly. Only because we can look back to the early stages of the assembly, which is not possible with other techniques, or using a technique where we freeze the sample and disrupt the assembly process and then look at it using electron microscopy or any other technique. So, and also when we do as a proof of concept, when we use particles which should have bigger capillary type of interactions, we again we got much more pronounced interactions among the particles, and we could observe these stacks forming on the surface of the liquid. And here again we are getting very good contrast here because we have a hematite core, which is the iron oxide phase, and when we look at the high magnification image, we notice again it's a directional assembly, and because particles are still in motion, we observe that these stacks are flexible, which is an important detail for us because it tells us that the interaction among the particles are weak, and that they can be, so these stacks change their curvature with time but still remain intact. So our studies told us that capillary type forces dominate interparticle interaction, because we could look at the assembly process from the beginning to the end without disrupting the assembly, and could track that what are the building blocks of the final morphology. And that's not possible with the other techniques where we have to stop the process in order to look at this. So in summary, using this electron microscopy imaging technique, we are getting high enough resolution to look at the position and orientation of each and every particle. While they can be in motion in case of a dilute assembly, or as shown here in this jammed assembly where particles are barely moving or not moving at all. So now with the understanding developed from these observations, we are looking forward to other liquid systems where we can have other surface chemistries and other viscosities, which is an important factor for this type of studies. And we are also trying to understand the effect of, or if there is an effect of electron beam when we are looking at the dynamics, because when we are looking at the structure, it's not a concern because we don't see any observable artifact. But when we are looking at the dynamics, we need to take care of any possible effect of electron beam also. So that's something we are going forward to look at. And another advantage this process is giving us that although we are looking at the sample locally, we can look at much a big sample. We can look at different spots, and we are not destroying the overall sample. And that gives us the capability of having a reliable and broad set of data from a single sample. So usually these samples are in millimeters in length, and we image these areas around 100 micrometers squares in a single frame. So we have a reliable understanding of the sample, because we can look at across the sample, as SEM allows us to put a large sample in, unlike other techniques where we have to confine it and have to use a small sample. So with that, I hope I could convince you that the electron microscopy can be used with the liquid samples successfully, and SEM is also okay after doing all these studies. So with that, I want to thank you all, and I'm happy to answer any questions.
Thank you, Satyam. Thank you, Alex. That was great. If folks have questions, please feel free to unmute yourself or put them in the chat and we can read them for you.
Andrew, I have a pre-submitted question.
Great.
What is the smallest particle size you can use?
Yes, so we have looked at particles as small as 20 nanometers when we have a dilute assembly. So particles are still in motion, so we have to focus on a moving particle, but still we could look at the particles which were about the size of 20 nanometers.
I have another one. What other liquid systems have you tried with SEM, STEM, and have you looked at polymers?
Yes, so we have tried polymer crystallization and from solution in studying it using SEM. And we also use TEM to study that. So we looked at polyethylene glycol crystallization from solution. And if I can show that. So we looked at polymers and their crystals in very thin liquid, ionic liquid film, and again without any confinement. So these are TEM images, and we did the same with SEM also. So we could identify these nanocrystals of polyethylene glycol and how they form these networks using SEM and TEM.
Looks like we have some audience questions. I think Manasi, you were first. Please feel free.
Hey, thanks, Alex and Satyam. Those were great talks. So I have two questions. The first one is, what are the typical dose rates that you use for these studies? For the particle assembly studies, what are like the typical dose rates?
So we, if Alex wants to answer this question, so we—
You want me to answer it? So the dose rate is much smaller than CryoEM typically. Much smaller because it's SEM. So we scan extremely fast, and the probe size of the probe current is very small. So it's orders of magnitude lower than CryoEM. So and we observe literally no contamination or damage or anything like that.
And how long are these experiments? I mean, if I'm thinking about the total dose that is kind of impinged on the sample.
Yeah, don't forget, so the ionic liquids are conductive. So to some extent, so they have ionic conductivity, so we can get rid of some of the electrons slowly. And we don't pump a lot of electrons. And that liquid is in motion. So we have actually a current, it's kind of grounded. It's not perfectly grounded, but 15 minutes, right, Satyam? 15 minutes or so is not a problem at all. And yeah, in the TM, it's very fast. TM crosslinks very quickly. So in STEM, it's a little bit slower than in wide field illumination, but for SEM I actually think it's like if you could pay for the instrument time, you can keep it running for quite some time. So we never tried. Okay. It's because nobody wants to pay for it, but
understandably.
but I think under the conditions, I think we never really observed anything freezing. So if it doesn't freeze or it behaves the same way, it follows the Stokes-Einstein behavior, So I would say there's no real negative impact. I'm not saying that locally you don't get some cross-linking within the ionic liquid. That just will happen. But it probably in the beginning, it will be so little that it will eventually dissolve in the rest of the pool of the ionic liquid, but since it is relatively large.
Yeah, because it's really interesting to see the diffusion coefficient, which is close to the free diffusion, which is not really typical, for instance, in liquid TEM experiments because of surface. So that was really interesting and useful observation. Yeah.
That's why we started doing SEM.
Leo, feel free. You're still muted.
Oh, hey, this is Leo from MIE department and CPHM. I have two questions here. So first one is, what is the mechanism of those nanoparticles moving towards the surface, but not staying inside the surface? Is there because of the hydrophobicity or hydrophilicity of the particles coating, or is something else? The second question is, what if we replace the ionic liquid with basically liquid metal, which is a more conductive fluid, and it's basically also very, very conductive in like much more conductive compared to the ionic liquid. So these are my two questions.
Yes. So for the first question, this is diffusion based. So particles diffuse from the bulk to the interface. They are not exactly driven to the interface. It's when they diffuse and reach the interface, they absorb there. It's mostly because of the ligand grafted to the surface. So for polyethylene glycol, the ionic liquid is a marginal solvent. It's not a very good solvent, and it also has a lower surface energy than the ionic liquid. So when they reach the interface and absorb there, they are perfectly stable there. So we don't really see a desorption process where particles goes back into the bulk again. So when they reach the interface, they are stable. So we control the concentration at the surface using concentration in the bulk. I hope that answered the question. And the second question, so I'm not sure what kind of viscosity we will be getting with the liquid metal. I guess it would be really high. So one of the concerns from our study was we needed a solvent which had a lower viscosity. Usually ionic liquids also have a very high viscosity. So this particular choice had a good viscosity. Still, it's 100 times more than water, but it was good enough for our study from the experimental time scale. So I guess it can be done, the liquid metal. For our particular case, it might be a very slow process to observe anything, like to track the diffusion and then observe the assembly process. So it might be too slow, but I guess it can be done.
So most likely the liquid metal has very similar viscosity compared to water. It's not as low as water, but definitely much lower compared to ionic liquids. And it has much higher surface tension. Yeah, it has much higher surface tension. So it's probably impossible, almost impossible for you to put those particles inside liquid metal. It's automatically on the surface already. So it's a direct observation of their interactions on top.
So
probably,
as long as it's not toxic, I put it in the microscope. So it's a try and error type thing. I like the idea. I think that's a very good idea. But there are restrictions. For example, I was thinking about mercury at some point, but EH&S would probably not be happy about it. I think that's we never thought about it, but I think this is very interesting idea. And doing literally hard materials that way. It's hard, soft materials. It's still soft, but it's a hard material. It's not a polymer, right? So I think there's potential behind that. It's just my guess.
Mm.
I would like to try it.
So Leo, that might be a good spot to talk about, some of those seed mechanisms. Maybe there's a pilot type project we can figure out there how to get you guys working together.
Right. Probably you'll see a seed proposal coming in.
Look forward to it. Lisa, do we have any other pre-submitted questions?
I have one more.
All right.
How deep can you detect particles below the IL surface with your technique?
We roughly around 5 to 10 nanometers, as much as 15 nanometers we could see. So that's one of the reasons when we have partially adsorbed rods, we can see its submerged part because we can look deeper inside the liquid. So somewhere around 5 to 15 nanometers for these imaging conditions.
Yeah, essentially it depends on the acceleration voltage we're using. There's of course a limitation. If we go too higher, then we eventually will get cross-linking. So we can tune it a little bit. Depends on the excitation volume.
Any additional questions?
Oh, can I ask one more question?
Of course.
I was wondering if have you tried ionic liquids in TEM?
Oh yeah. They cross-link so fast. It depends on the ionic liquid. They're not all the same. STEM is a little bit better because but then it gets really noisy. But still it cross-links relatively fast. And then in TM, we have the confinement to a relatively small space. So if we put it on a lacy carbon or something like that, so we are stuck somehow with that area of one hole in the lacy carbon. So there's not a lot of movement. So a lot of times the particles, they just adhere to the edges of the carbon, which is also like 30 nanometers thick. So it does look in the TM like that, but it has a height into it, right? So you get some kind of attractive forces there or repulsive forces, which doesn't help really studying the interaction between the individual particles. I think it's more of with STEM, you can actually do a lot because the image, just like in SEM, doesn't have to be noise free, right? So we can scan at 25 nanoseconds in the STEM like we can scan in the SEM. It's just the volume. We don't have the volume. That was most of the time that what restricted us. And then the particles ended up at some edge and you don't really know exactly where they are, right? So, but we did a lot of work on the ionic liquids. The crystallization he showed in the TM, that worked pretty well, I thought. But it was kind of the only thing which really worked.
Yeah, recently there are some other studies from where people have looked at micelles in ionic liquid using TM. So it's possible, but in every case we freeze the motion and we freeze the structure, but we can see it without much damage to it.
Any other questions? Thank you.
That's well said. So I want to thank you all for attending today's seminar. Our next seminar is scheduled for Tuesday, April 6th, featuring atomic force microscopy with staff scientist Keith Dussault. So we save the date and hope to see you there. I hope you get out and enjoy this beautiful day. Bye.